The next talk will be presented by Hasib-Al, Ph.D. student from University of Maryland and a research scholar at Johns Hopkins University. Hasib, please share your screen. Hasib's talk is titled ViT at Edge, Distilled Vision Transformer-Based Foundation Model for Efficient Edge Deployment. Hasib, the floor is yours.
Hello, everyone. I am Hasib-Al, discussing about ViT at Edge, Distilled Vision Transformer-Based Foundation Model for Efficient Edge Deployment. We are witnessing a major shift in computer vision with Vision Transformer or ViTs. Moving past the older CNN model, ViTs are setting new standards, making our vision technology not just better, but smarter and more efficient too. However, there's a catch. The sheer computational heft of these state-of-the-art models make their deployment on mobile or edge devices a daunting challenge. Just consider this. A model with 1 million parameters requires about 3.8 MB in their full precision version. Now scale that up to the tens or hundreds of millions of parameters common in leading ViT-based models, and you see the dilemma. Now, let's pick a classic computer vision challenge, making low quality images crystal clear, known as image super resolution. For years, this task has not been just about improving the picture quality, but also opening up new opportunities in the fields like security, healthcare, and even on our own smartphones. The integration of ViT-based foundation models into edge computing is generating significant excitement, making the pivotal movement in how we process and analyze the data directly where it is generated. The realms of edge machine learning and tiny machine learning are at the forefront of this revolution. By optimizing AI models for low-power devices, we are not just enhancing efficiency, we are minimizing the latency and power consumption. Our goal is clear: to harness the power of ViT-based foundation models at the edge. This ambitious endeavor aims to seamlessly merge high computational performance with energy efficiency. Through our innovative approaches, we are not just narrowing the gap between power consumption and AI performance. We want to run the models on the on-chip memories of these heterogeneous edge devices for minimizing the latency and power consumptions. Building on the momentum from our previous discussion, we want to develop a ViT-based solution for image super resolution task for edge, which can be edge deployable. Our evolution metrics for this particular task would be peak signal to noise ratio, also known as PSNR. So the main contribution for this particular work is pre-training ViT-based foundation models from scratch, and then compress the pre-trained model with quantization, pruning or sparsification, and knowledge distillation. This is the figure that illustrates a commonly employed high-level network architecture for image super resolution tasks. It comprises three integral components: a shallow feature extraction module, a deep feature extraction module, and an image reconstruction module. The shallow feature extraction module usually employs a small number of convolutional layers to extract the shallow features containing essential low frequency information. The core network lies within the Swine transformer, a specialized vision transformer based deep feature extraction module, which meticulously obtains intricate and high levels of feature, collectively holding the pivotal role in shaping the system's overall performance and capabilities. Ultimately, both shallow and deep features converge within the reconstruction module to facilitate the creation of high-quality image reconstruction. As we can see here, the model size clearly shows that it can't be deployed on the on-chip memories of the edge devices. So we require model compression techniques for efficient deployment. Model compression techniques like pruning and quantizations are essential for fitting those large ViT-based neural networks onto mobile devices with limited resources. For example, quantization, which reduces the model sizes by converting its data from high precision format to simpler integer forms, making it less demanding on the memory and processing power. Pruning eliminates the unnecessary model parameters to make it lighter, but it can lead to a less uniform network structure that might need extra memory for organization. Structural sparsity solves this problem by recognizing the network to efficiently uh, incorporate this cache, removing the need for additional memory to track the structure. And merging pruning with quantization can also significantly downsize the neural networks while preserving its functional integrity to a satisfactory level. And then it comes to the knowledge distillation, where we can use the larger model as a teacher to instruct the training process. The main idea is to minimize the divergence between the teacher and students' probability distribution. Using these techniques, previously we have developed a wide range of CNN-based multimodal applications for edge devices. In one of our previous work, we used mixed precision quantization and cyclic sparsification to reduce the memory consumption to almost 13 times on the FPGA-based edge devices. In another previous work of mine, I have used knowledge distillation and quantization. I could reduce model size up to 296 times from its original models, so it can be edge deployed. And for this particular work, I have actually deployed on microcontroller-based edge devices, a GAP8 processor. Very recently, this year's tinyML conference, I have an accepted paper that uses knowledge distillation and quantization to reduce the model size to 1400 times, maintaining the comparable performance. This was for a visual question answering task. So based on all of my previous CNN-based results, I have run the similar experiment for ViT-based image super resolution task, where I could reduce the model model size to 582 times at the cost of only 0.66 decrease in PSNR from the original swine transformer-based image reconstruction model. So we have used diff2k dataset for our experiments. So the knowledge distillation and 8-bit quantization we have used to compress this model, as I have mentioned already. This 81 kilobyte of model can clearly fit on the on-chip memory of the edge devices for low latency and low power edge deployment, as you can see from my previous slides. So yeah, that's it. So this is the ViT at Edge, which develops the compressed computer vision models for edge deployment. We have used knowledge distillation and quantization specifically to compress the model. Further compression is possible if we can use state-of-the-art sparsification techniques. From our own experiments, we got 582 times memory reduction at the cost of very minimal performance degradation. Thank you, everyone. You can contact me in my emails, or also I am here to answer any questions.
Thank you very much, Hasib, and thank you for staying on time.
A big thank you again to all of our sponsors that make this possible. In particular, thank you to the executive strategic partners of tinyML, Qualcomm AI, advancing AI research to make efficient AI ubiquitous, also Sentient, making edge AI a reality, the platinum strategic partners, EmbedUR, Sony AI to deploy vision AI at the edge at scale, the gold strategic partners, ARM, Edge Impulse, Infineon, Renesas, ST Micro, and Synaptics, and the silver strategic partners, which we have here, AIZip, Arduino, BrainChip, bFission, Greenwaves, Gravity, IMAX, Imagimob, Initera, Noda AI, NXP, Procter & Gamble, Schneider Electric, SensiML, Silicon Labs, and TDK. So that concludes our first day. Don't forget, we have a lot more action-packed agenda for tomorrow as well, starting at the same time. So that concludes our session for today. And thank you for joining, everyone. See you tomorrow.